This is not good because this is what is going to cause loss circulation. It's going to cause losses in drilling mud, especially if you're drilling offshore. The drilling mud is not something that you can get. It's not cheap to get. You need ships in order to deliver the drilling mud. So you don't want to get into these events. However, there is another case. If you calculate a value in which PV is smaller than your minimum principal stress, and somehow you get at one point to drill with a pressure PW which is higher than PV but smaller than S3, because PW is higher than PV, you're going to cause a tensile fracture. But this is going to be a short tensile fracture. It will not propagate because your minimum principal stress is higher than the pressure of the mud. And because of that, they'll propagate just a very short distance, which is the distance or the area in which the wellbore modifies stresses, but it won't propagate far, and this one will not compromise wellbore stability. And actually, these type of fractures are the ones that we saw in these images, which are there. Those are tensile fractures. They were caused by the action of drilling, but they are short and they do not propagate far, and it is fine. It is fine to have those. So it's very, very important to recognize this difference, because if you are above this value, then and if you eventually run into values higher than PV, say because you didn't calculate well the value of tensile strength, or you saw there was a rock which was not fractured but it tended to be fractured, then by drilling at the pressure higher than S3, you could run into these problems of loss circulation. I think we're very close to finish, so I'm going to try to finish in the 3 minutes that we have left, and probably will revisit some of the concepts next class. So far what we have done is we have calculated limits for the mud window, or what we can also call an upper bound and a lower bound. So if you wanted to drill in a given location, now with the equations that we have seen, you can calculate in terms of equivalent circulation density, which is going to give you the mud pressure. So PW is a function of the equivalent circulation density and also depth. And here I'm just plotting equivalent circulation density. We have determined two bounds. One, it's a lower bound, like for example could be PWBO, the lower pressure that we can get to without causing shear fractures. And we have also calculated a maximum value, which this is going to be an upper bound the maximum value that you can get to without compromising wellbore stability. That, for example, it's going to depend on other variables, but for example, we could set it to the value of PV. So now everything that we need to do now is just to design the casings that are going to go into there. So basically, what you want to do is you want to drill an open hole section with a constant mud density so that you don't produce shear fractures, you don't produce tensile fractures. So if you have a constant mud density in an open hole section, let's say that we start here at this value of mud density. So this value is going to barely make a little bit of tensile fractures on the top. And if I'm drilling at a constant density, this is going to be a line like this. And if this is a constant density on the top, while this is open, I'm going to cause a little bit of tensile fractures over here and a little bit of shear fractures over there. I cannot go any deeper, because if I go deeper, I'll have a lot of shear fractures. So at that point is at the point in which you set your first casing setting depth. So at that point, you stop drilling, you put casing, you cement it, and at this point, you may also want to run a leak-off test. A leak-off test, something we didn't mention, but a leak-off test is going to be an upper bound for drilling. Usually, you can make some calculations about what you think is going to be your upper bound, but there is a lot of uncertainty in these geological systems, a lot of uncertainty in determining what is SH max, SH mean. So you may just want to do a test and check what is the actual value. And probably you can fix your upper bound to be a more accurate value. So after you get there, then you put the casing and you run into the next section. Same as before. Wait a minute, this came out a little bit inclined. Same as before. Now you can go up to this length, and this is the point in which you set your next casing, and so on. Probably here, this is going to be the last point in which, let's say that you're getting into this formation, then you lower the production casing, you do perforations, and that's the end of your casing design. So last thing I'm going to say here, your objective is to calculate this lower and upper bound so that you have a wide window. The bigger the window, the less number of casings you have to put. If you have a very short drilling mud window, can you see that you will have to do a lot of these things in order to get to the bottom? So you will have to put a lot of casings. And putting a lot of casings, first of all, it's expensive, takes a lot of drilling time, and third, you're going to have to reduce a lot the diameter of your production casing, which is not going to be good either. So bigger, wider windows are going to come from understanding the geomechanics of your rock well, and trying to enlarge that is going to save a lot of costs for drilling. All right, guys. Have a great weekend. Work on the homework. Let me know if you have problems. And I'll see you on Tuesday.